This is tutorial 12 again, part 4. So part 4 will be devoted to the problems, question number 3, 4, and 5. These problems are about calculating contour integrals of complex variable functions. Let's write down this topic. So contour integrals of complex variable functions. Complex variable functions. So usually these integrals look like this. F of z is a complex number, as you know. And here you can see the name of the notation of some curve, some path, where L is given path, just like for work integrals. So you need to calculate this integral along a given path from point A to point B, from some start point to some end point. But most of all, the favorite integrals here in complex variable theory are actually integrals on closed contours. These are the favorites. And so maybe then we can use the different notation, C closed. And so where C is a closed contour this time, we can make a drawing just. So this is our complex plane. And here you have this closed contour C. And the direction is usually considered to be counterclockwise by default. Otherwise, it would be pointed out to you explicitly. Okay, so how can this integral can be calculated? It turns out there are 3 methods which you need to master in this particular tutorial. 3 methods. So the first method, let's call it method 1. It's the path parameterization. Path parameterization method. Sounds very familiar, actually. Path parameterization. It does sound familiar for me because we use the same method for work integrals. In general, these integrals of complex variable functions and work integrals have a lot in common, but we are going to discuss it later. Now, my task is to outline you the main 3 methods which we need to study in this tutorial. The second method is called Cauchy's integration formula or integral formula. Cauchy's integral formula. Cauchy's integral formula. This is going to be the second method. And finally, the best and the most general will be called Cauchy's residue theorem. Just residue theorem. So the whole point of studying residues of functions in singularity point was actually to be able to integrate functions actually afterwards. So that is why all the previous material was sort of preparation for this global topic. And also the last 2 methods are suitable for integrals along closed contours only, whereas the first method is universal. It's suitable for ordinary paths which are not closed at all, as well as for closed paths. So let's start with the first method. Now you see the outline of our whole lesson. Okay, let's start with the first topic, path parameterization. Parameterization. And let me start with some very small and nice example. Let it be example 1, something really very simple, something like integral of imaginary part of z, dz. So that's how my integral looks like. And where L is a given path, and L, it's better to take black actually, where L is actually this section of parabola, very well known parabola for you, from point A11 and let's say to point B with coordinates 2 and 4. We can even draw a little picture. So this is our complex variable plane. So x and y, of course, are real and imaginary part of complex number, of course, as you can imagine. Okay, so where's our parabola? Parabola is here, and where's our section? So this is point A, let it be point A, and point B should be somewhere here. 1, 2, 1, 4 here. So this is our section, and we need to move in this direction. It looks, the even assignment looks very similar to the assignment given in the work integral. You always given, when you ask to calculate work integral, you always given a path, and you're given the direction in which you need to move along this path. Okay, let's see how do we need to approach this integral. You know, the idea is very simple actually. Wherever you see z, you can substitute z is equal to x plus iy, as simple as this. Okay, let's do it. So I'm substituting z, x plus y here, and also here. So as a result, we have an integral with two variables, x and y, just like in the work integral. And the idea is the same. The idea is to get rid of two letters, two variables, x and y, because if we are left with one letter only, x and y, we should be able to figure out how to calculate this integral. And at the same time, something unusual happens here, of course, compared to work integral, namely that you have this imaginary unit I. But you know, I is considered to be constant, just like everywhere else, so no problem with I. So what exactly can we do to get rid of one variable? Very simple idea, very old one actually. Wherever you see y, and you see y here and here, you can substitute the equation of parabola, so x squared. Maybe I should have simplified this. By the way, I forgot about it. Imaginary part of this number is just y. Let's simplify this. Okay, and now we can substitute x squared instead of y everywhere. X squared dx plus I x squared, and this is almost it. Of course, this expression does need some simplification, but the idea is simple as this. So we are left with only one variable, just like in work integrals, and that is why we need to see how does it change. It changes from 1 to 2. That's it. Not it, of course. We need to simplify this. We need to calculate this differential. But hopefully you remember that to calculate some differential of some function, d of f of x, you need to take the derivative of this function and multiply it by dx. So the rule is very simple one. So let's do it in the next line. So the derivative of the first term here, you can see the sum of two terms under differential here. So the derivative of the first term will be 1 and plus 2ix. 2ix is the derivative of the second term. So instead of this differential, I got this expression. And now we should figure out how to integrate this expression. But this is super easy. You can just do the multiplication first to prepare your expression. X squared plus 2ix cubed dx. And so we can write antiderivative of each term. So what is antiderivative of x squared? Of course, obviously, it's x cubed divided by 3 from 1 to 2. And here you have 2I as a constant, as a coefficient, and x to the power 4 divided by 4 from 1 to 2. And now we can perform this calculation. So it will be 2 cubed minus 1 cubed. As you can see, I prefer to pull out 1 over 3, not to worry about it too much when I'm substituting these numbers, because this expression looks much simpler than the whole expression. And the same I prefer to do here. Here I have 2 and 4 get simplified a little bit. So I divided by 2 is my coefficient. And I need to worry only about x to the power 4. So 2 to the power 4 minus 1 to the power 4. That's almost it. And what do we have? 8 minus 1 will be 7 over 3. And here we have I times 15 over 2. So that's it. This is our answer to this problem. As you can see, the technique is very simple one. It's amazingly similar to that of the work integral. And you know what's more? what's more, even the properties of the work integrals and properties of these integrals of complex variables are pretty similar. So, but you know what? We need to discuss a little bit, not even discuss, just to refresh our memory when it comes to parameterization of curves. How can you do parameterization of curves? So in this particular example number one, I didn't do actually any parameterization. I just substituted x squared instead of y. We do know what how to parameterize curves. Let's discuss it a little bit. Parameterization of curves. How can it be done? So let's start with our parabola. So this parabola, y is equal to x squared. If you prefer to introduce new parameter, you can do it this way. You can denote x by t, and then your y will be t squared. If you prefer variable t, parameter t, you can do it this way. But this solution was quite convenient as well. So it's completely up to you. Okay, so if you're dealing with explicit function where y is expressed in terms of x, you can leave it as it is and use this approach which I showed you before. Or maybe you can just introduce new parameter if you find it more convenient, more beautiful. But what about, there's always some difficulties concerning circles. So how do we go about circles? So circle usually in the past when we dealt with the work integrals, we used to rewrite this circle. This is the Cartesian equation of circle. We would rewrite it in a parametric form: r times cosine of t, and y is r is times sinus t, and t plays the role of the angle, and that is why if you're interested in the whole circle, your angles should change from 0 to 5. So you can still use this old technique. But you know what? Maybe you want to be a little bit more advanced. We are studying now a new field of mathematics, complex variable theory. So maybe it makes sense to give you some, just more advanced notation. Nothing new about this idea. So, for example, here in complex variable theory, the equation of the circle could be rewritten as this. So this circle is equivalent to this circle. But you know what? It's not very convenient to use it in this form because it's highly unlikely that you come across modulus of z under your integral. And that is why parameterization could be done in this way, but it's this much more convenient form. Look at this. Z could be written as r, this is constant, this is your radius, e to the power of I, maybe theta or phi, it doesn't matter. So it looks more convenient. You need to introduce x and y first. You can directly substitute z with new variable theta or phi or whatever. This is the polar angle or argument of your complex variable number. So this, how can you do this transition? So this is for the circle with the radius r, and center in the origin. This more general circle should be written like this: z minus z0 is equal to r. So in this case, the center of the circle gets shifted. It's not in the origin anymore. It is in some point z0, but the radius is the same. Radius is r. In this case, your parameterization will look a little bit different. So z0 plus the same equation as you had here. So maybe this parameterization would look more appealing to you because it could be done sort of in one step. You immediately change your variable z for variable theta, and that's it. But if you prefer to use the old technique, which we studied in work when we discussed work integrals, you will have to make transition from z to x and y first, and then instead of x and y, you can substitute this parametric equation. It doesn't matter actually. So I suggest that we solve question 3 from our tutorial sheet now. Question 3 from our tutorial sheet now. In this tutorial, this question, you are given integral alone closed contour, which looks like 2z divided by z squared plus 4 dz, where C is the closed circle of radius 1. You need to recognize this equation. So I prefer to make drawings all the time, even though sometimes they are not needed so much, but it just gives me peace of mind when I can see the whole contour. So this is our contour. And as we just discussed, we can immediately do parameterization. Instead of z, we can substitute this expression, which in our case, phi, I prefer to write phi, not phi, theta. In our case, as the radius was 1, we can just substitute this guy. So instead of z, we can substitute e to the power of I theta. And of course, our theta is angle. And as we need to do the whole circle, we can write that we are moving from 0 to 2 pi. Okay, let's make this substitution. So I'm continuing writing here. So what do we have? 2 times z. Instead of z, I'm substituting e to the power of e theta divided e to the power of e theta squared plus 4d. And instead of z, I'm plugging in this guy here. And as you can see, even though this expression looks a little bit fancy, but nevertheless, we can observe a very nice phenomenon. We are left with only one variable theta now. And there is, hopefully, this integral will be much easier to calculate, who knows. So, and we already discussed that theta changes from 0 to 2 pi. That is why we can continue this integral. What do we need to do in the first place? We need to calculate differential of this function. So we need to take the derivative of this function e to the power of I theta times I and d theta. And I'm rewriting the denominator e times e theta squared plus 4. So, and after that, what can we do after that? After that, we can do some simplification. We can observe that 2i is a constant. It could be pulled in front of integral. And here we have e to the power of these powers get added together, 2i theta d theta. And here I can apply the very well-known property of the powers. It's actually the same expression, 2i theta plus 4. So this integral now looks like, I should use the new page because otherwise I'm running out of room here. Okay, so 2i is in front of the integral times 2 pi. What can you do with this integral? What can you do with this integral? You can actually use the very good property that this guy, so this expression could be viewed as the derivative of function, which was used to be here. So we can put this expression back under the differential, but then in this case, it will turn into its integral, into its antiderivative. So it will look like 1 divided by 2i e to the power of 2i theta divided by the same expression plus 4. So we can observe that these two constants get cancelled out. So we are left with this integral d of e to the power of 2i theta divided by the same expression. And you know what? It's almost the very well-known integral. If you add plus 4 here, so the expression under differential will become the same as the expression in the denominator. It means that we are dealing with a very well-known integral. Dx over x is the logarithm of modulus x. You should remember this integral, or you can easily Google it for it. Okay, so our antiderivative e to the power of 2i theta plus 4, and our limits of integration should be substituted as well. So let's do it. So what happens if you plug in 2 pi instead of this? We will get 4i pi plus 4 minus I, and now I'm plugging in 0 instead of, so it will be 0 plus 4. So as you can see, 4 and 4 gets cancelled out, but what about these two guys? Maybe it's better to rewrite it like 4 pi I minus e to the power of 0. You know what? Actually, they symbolize the same number. This number is given in exponential form. So both numbers have radius 1, so they are both in the on the equation with the radius 1. But as for angles, this guy has angle 1, so it's actually, this is number 1, actually, real number 1. What about this guy? Where's the angle 4 pi? You know, 4 pi means 2 rotations here. It's the same. So it's also number 1. So our result is 0. Our result is 0. So we did this integral in this way, using path permutation, because we were just explicitly asked to do so. But you know what? So maybe you noticed that maybe it wasn't needed to do it in this way. Maybe there was a much easier way to calculate this integral. Let's discuss the similarities and maybe some differences between work integrals. Let's discuss work integrals in the left columns, work integrals, and complex variable integrals. Let's compare them. Complex variable integrals. So it will be very interesting to discuss them. So let me remind you how work integral look like. They look like p dx plus q dy. This is a 2D case, of course, and I'm comparing only with this 2D case. And here we have something like f of z dz. Of course, p and q are not constants, as you may remember. These are functions of two variables, x and y. But what these guys, two different integrals, have in common, they both are taken along some given path, But you know what? Maybe you immediately recalled that when we were dealing with work integrals, there was a nice property. Sometimes these integrals, the result of calculation, didn't depend on the shape of the curve, and it depended only on the start and ending point of the curve. Where did it happen? When the vector field, do you remember this p and q were components of your vector field? This vector 2D vector field. So if this vector field was irrotational, namely in the 2D case, you know this shortcut dq over dx was equal to dp over dy, that meant that then your integral, let's call it I, you were supposed to find so-called potential of this vector field and substitute the start and the end point. So it was given like phi in the end point minus phi at the beginning of your path. This was a very nice property. And moreover, so this was just along some path from A to B. But in the case of, we can write this phrase, moreover, if this integral was along some closed curve, p dx plus q dy. In this case, it was just equal to 0, because in the case of closed path, your start and end point are the same. So this was a very beautiful property. So if you were given an integral along closed path, and your vector field was irrotational, that you could have given answer immediately, just 0, and that's it. And that is why it's interesting to discuss if there is a similar property here in the field of complex variable. And the answer is yes. But it's not completely, it's not 100% similar, but maybe 90% similar. So what happens here? It turns out that if f of z, analytic function, you know what? It's not actually necessary that this function is analytic on the whole complex plane. It's pretty enough that it's analytic in some region which contains this curve. So analytic, we can maybe on curve L, Then it turns out that this integral doesn't depend on the shape of this curve, connecting this end and start point. It only depends on this start point and on the end point. But what can we calculate instead of this potential function? In this case, you just calculate this antiderivative, just integral function, and you substitute the start point and the end point. We can rewrite it as a very well-known rule from your previous calculus. And of course, similarly, if you're dealing with the integral along closed contour, closed curve, and your function is analytic, you can easily make this conclusion, very beautiful conclusion. So it looks like it's very handy to know these beautiful properties. And you know what? Now we can discuss some very small integrals, trying to apply these properties. Let's call it example 3, but actually it's gonna contain some like 3 sub-examples. Let's consider the first example, integral along path L z squared dz. What can we see? Yeah, and I haven't discussed one more important thing. Let's get back to this page. But the question might arise that, okay, in the case of work integrals, to check that we can apply this beautiful property, we have this beautiful equation in 2D case, of course. In 3D case, it was just a calculation of rotor, of curl of the. But what can we do here instead? We need to check that our function is analytic. And you remember from previous lessons that there was an assignment which sounded like you are given a function f of z. Let's check if it's analytic or not. Generally, you need to apply to check so-called Cauchy-Riemann conditions. Cauchy-Riemann conditions. Cauchy-Riemann conditions are Cauchy-Riemann conditions. Riemann conditions. Let me remind you how they look like. U prime x is equal to v prime y, and u prime y is equal to minus v prime x, where f of z could be viewed as u plus I times v. So u was the real part of this function f of z, and v was the imaginary part. But you know what? It does not look like very easy. It's very easy to check it. But if you get a lot of experience, there's no problem. But is there any shortcut or quick way to determine if your function is analytical or not? You know what? There are some hints, actually. There are some hints. If function f of z contains some weird things which which you can find only here in complex variable function. For example, z conjugate, or maybe imaginary part of z, or maybe real part of z, or maybe what else can we do? We have moduluses and others. It means that this function is not analytic. This is 100% guarantee is not analytic. And that is why you can't calculate it like an ordinary function. So let's go to our function. But you know what? Our function, I have given you the line. Let's use the same line probably for all my examples. So let it be parabola again. Let it be parabola again from the last example. So parabola y is equal to x squared from point 1, 1 to point 2, 4. Do you remember this example? Our first example. So let's imagine that we are given the curve, the path. The start point is A1, 1. Maybe it's better to rewrite it here. And the ending point is B2, 2, 4. And you ask to calculate this integral. Of course, you can always use this path parameterization. You can substitute x plus I times y instead of z and do everything which we did in our previous examples. But you know what? This function is 100% analytic because it doesn't contain these weird things, and also it doesn't have singularity points. That is why we can treat this function as ordinary function from our past. So what is the antiderivative? Z cubed divided by 3. And all you need to do now, you need to substitute a and b, just according to this famous rule. So let's do it. B has coordinates 2, 4. We need to rewrite b and a, by the way, because we are in complex variable. So point A has coordinates 1, 1. What does it mean? It means that this is the number 1 plus I, of course. And as for b, sorry, I made a mess here. And as for b, it has coordinates 2 plus 4. It means that this is number 2 plus 4i. Sorry for this mess. It's better to rewrite it here. So the start point is 1 plus I, which is point A, capital A. And the end point in this one. And all we need to do, we just need to substitute this point here and calculate the result. But you know what, I'm going to save our time. I'm not going to calculate it. You know pretty well how to do it. My idea was just to show you how lucky you are when you're dealing with analytic functions. You don't need to worry about this parameterization and everything. You can just act just like before. But you should be absolutely sure that this function is analytic. Next, let's do one more example. The same path, but the function is different. So z conjugate dz. Aha. And let L be the same path. In this case, no. In this case, no. This function does contain something really weird, which we never came across before we started studying complex variable theory. That is why I don't think it's analytic. We can, of course, we can apply and check Cauchy-Riemann conditions, but I'm pretty sure that it's not analytic. So what we need to do, we need to remember that z conjugate is x minus y. We need to substitute x plus y here, and so on and so on. And after that, we need to perform this path parameterization, and so on and so on. So now you see how you can treat these integrals. And of course, and the last example within this example 3, let's imagine that you're given integral of this function z minus 3 divided by z plus 4 dz. And the path is written here. So this time we are given the integral along the closed path. And this is, of course, this familiar circle. This is the circle of radius 1, and the center of the circle is in the origin, of course. But what about the function? It doesn't look like it's an analytical function. You know why? Because it has a point of singularity, -4. As we discussed before, it's not allowed to divide by 0 in any field of mathematics. So we do have trouble here. We do have a problem here. But you know what? In reality, we don't have. Because it turns out that in complex variable theory, only those singularities matter which are inside the circle. So this is our path, this is circle, and our singularity point is outside this circle. That is why we don't care about it. So it means that this function f of z minus 3 z plus 4, it's analytic inside the circle, and that is why it's just the result is just 0 according to our previous page, our previous table. So if your function is analytic inside this closed contour, so you can easily give the answer 0, just 0. So this sounds very beautiful. Okay, it's time to wind up with part demonstration because there are still 2 more topics waiting for us. So the second topic will be Cauchy's integral formula. Let's write it down. Cauchy's integral formula. Cauchy's integral formula. So it's only for integrals along closed contours. They play a bigger, huge role in complex variable theory. So let me write it down immediately for you. So you are given integral along the closed contour. And function which is under the integral should have a very specific form, very specific shape. It should look something like this, dz. So C is the closed contour. It's better to draw it here, the contour. So this is our complex variable plane. And here we have this closed contour. The shape doesn't matter. And moreover, so this is your contour, closed contour, and this z0, which is a singularity point, should be inside the contour. This is super important here. This is actually crucial. In this case, this integral is equal to 2 pi I times f n of z0, where fn means the derivative of the nth order, And of course, I need to highlight again that z0 inside contour C. This is super important. So, as you can see, there is a very beautiful way not to find antiderivative or do part computation. You can just have a close look at here, the shape, the layout of your function. And if you spotted that it does observe this requirement of being, the same shape, so you can just calculate it as the derivative of nth order. N is here. You can find here of this function which is in numerator. Very beautiful method actually. So let's start. And moreover, this function, this formula looks very beautiful actually when n is equal to 0, because n is equal to 0 means the derivative of 0 order. It means no derivative at all. It's just 2 pi I times f of z0, as simple as this. Okay, so let's start with some beautiful example. So I'm going to enumerate examples from the very beginning. So this is going to be example 1 again. Example 1 for this part 2. Let's try and calculate integral or along contour z of function e to the power of z divided by z plus 1 squared dz, where contour c is just the circle of radius 2. Circle of radius 2 with the origin, with the center in the origin, of course. So let's compare this our expression with this general expression. Does our function look like this? You know what it does? So this expression in the denominator plays the role of f of z, and the expression given in the denominator plays the role of z minus z0 in the power to the power of n plus 1. So in our case, n is equal to 1, of course, obviously. But what about z0? Z0 is equal to minus 1. And we need to make sure that minus 1 is inside our contour. But you know what? We are quite lucky because minus 1 is somewhere here. It is inside the contour. So it means that we can apply this beautiful Cauchy's integral formula. Let's do it. So it will be, the answer will be 2p times I. F, what is the order of derivative? The first, because n is equal to 1. F prime of z0 of minus 1. So we should find the derivative of f of z, but it's super simple. Derivative of the exponent is the exponent itself. So derivative will be e to the power z, the same. But we need to calculate it in the point z is equal to minus 1 in our singularity point. So what it will be? 2pi and times e to the power of minus 1. So this is our answer actually. If you're not quite happy with it, you can simplify it a little bit. Maybe it will look a little bit more beautiful. So things could be as simple as this. Okay, this was the first example, but now I'm going to give you the second example. Sometimes maybe things look much more trickier and you might get under the impression, oh no, in this particular case, it's absolutely impossible to use Cauchy's formula. But it's not always the case. Let's consider the second example, which looks a little bit more daunting. It's better to use red. Okay, so again, integral along the closed contour C, and here we have quite fancy expression, z squared plus 3iz plus minus 2 divided by z cubed plus 9z dz, and the contour is the equation, the circle with the radius 1. I'm going to draw it somewhere here. Okay, so but you know what? It feels like our function doesn't look like this anymore. It doesn't, it doesn't meet these requirements of this. It should be of this form, as we discussed before. But you know what? We can organize some things sometimes. I think that we need just to simplify something in the denominator. Maybe we'll be lucky. So as for the denominator, it will get written all the time. So for example, we can pull out z out of this expression. And also, we will have z squared plus 9. What can we do with z squared plus 9? Before you started learning complex family of signal, you knew that you can't do anything with this expression. You can't factor it. But here in complex variable theory, it could be easily done. Z plus 3i minus z minus 3i. So let's do it. Let's substitute it. Z plus 3i times z minus 3i. So, but you know what? After this simplification, our function looks even more terrifying because we have even 3 points of singularities. But you know what? The beautiful thing is that you are interested only in the points which are inside the circle. So let's write down all our singularity points. The first one is 0, the second one is minus 3i, and the third one is plus 3i. And let's plot them on my, it's getting too small. Maybe I should plot it once again. Okay, let's plot this once again. So this is my circle. This is my contour actually. So where are my singularity points? The first one is just here, just inside the contour. But remaining two, look at them. 3i is here and minus 3i is here. That means that you shouldn't care about these points at all. They are not singularity points for you at all. Only the points which are inside the contour, they matter. So we are interested only in this guy, What does it mean? It means that all the remaining expression should be viewed as f of z. And you know what? I can even rewrite this expression to adjust it to our standard form. What can I do? I can rewrite, maybe I should use some yellow. So this whole expression plays the role of f of z. That's why I'm going to move it to the denominator. And maybe I should rewrite back this expression like z squared plus 9. So let's move this fraction to the numerator. So it will be z squared plus 9. And the guy which is in the denominator, let's rewrite it as z minus 0 to the power of 1. So as a result, this whole expression plays the role of f of z, and this expression in denominator plays the role of z minus z0 to the power of n plus 1. So we managed to rewrite our integral in the form which suits our needs, I should say. So what can we do now? So all we need to do, we need to realize that our n is equal to 0, by the way, because this is n plus 1. It means an n is equal. And our formula becomes actually super simple, actually, in this case. So according to Cauchy's formula, this is just 2 pi I times what? Let me show you this theorem. So we need to take the derivative of order 0. Derivative of order 0 means non-derivative at all. So it's just f at point 0. So our f is this red guy. So I'm rewriting this guy here. 3iz minus 2 divided by z squared 9 plus 9. And I should substitute z is equal to 0. That as simple as this, as you can see. So I think it's going to be super easy. This is 0, 0 minus 2 divided by 9. So this is actually our answer, but we can just a little bit simplify it. And that's it. So as you can see, the looks can be deceptive sometimes. Sometimes you get under impression, oh, this integral, let's have a look at it once again. This integral is super difficult. I definitely can't apply a Cauchy's formula here. But you know what? It turns out that you still can apply this formula here. Okay, so this was the second method, Cauchy's formula. Very beautiful one, but of course it has limitations. And the main limitation is that your given function should be of this particular form, nothing else. And that is why we need a more general method, which is the last one and the most general one, most universal one. Residue theorem method. Residue theorem is more universal. Residue theorem. So how does this theorem goes? So let's write down this formula. So let's imagine that we are given some integral along closed contour of some function f of z dz. And this function has singularity points where z1, z2, and so on, zn singularity points of this function of f of z, which are inside inside contour. Inside contour C. This is super important. Just like in the previous Koshu formula, which are inside the contour C. So I will put 3 exclamation marks here because it's super important. And I think the good idea, I'm not finished with the formula, of course. We're just discussing the conditions of this theorem. So let's make a drawing here. So this is the green one, our contour, our closed contour, C. And these points Z1, Z2, and so on, Zn, they are all inside your contour. You know what? Interesting thing, this function can have even more singularity points, Zn plus 1, Zn plus 2, but you don't care about them. You care only about those singularity points which are inside the contour. Okay, and so what next, you might ask me. The next is that in this case, your integral is equal to 2 pi I times the sum, let's denote it like sum from k to n. N is the number of points which are inside the contour. Residues of our function in these points zk. Maybe it's better to write it like this. So very beautiful formula. It's very easy to memorize it, no problem at all. What does it say? It says that if you need to calculate some integral over the closed contour from complex variable function, you need to write out all the singularity points and take those points which are inside your contour. Then you should calculate residues in these points which are inside the contour. Take the sum of these residues and then multiply it by 2 pi I. So as you can see, no limitation as to how this function should look like. It could be any function of any form. And then now you know, now the mystery has been resolved why so much emphasis has been put on all this theory about residues, about these singularity points, because the ultimate goal is to learn how to calculate these integrals along the closed contours. Okay, so now we can start practicing our skills. So practicing applying residue theorem. So what can we do? I can't find. Yeah. You know what? I decided to do the same example, but it won't be interesting, I think. I think it's better to do question 5a. Let's do question 5a, applying this theorem. So question 5a looks like this. 2z divided by z squared plus 4 dz. And contour is the circle of radius 4. So let's try and apply this beautiful theorem. So what can we do? First of all, we need to draw the contour, of course. This is a circle with the radius 4, quite a big radius. What about singularity points? We need to consider our denominator, put it equal to 0. And of course, you remember from the previous example that this expression to the left, now you can factorize it like z plus 2i times z minus 2i is equal to 0. So as a result, you have two singularity points, 2i and minus 2i. Now we need to plot them. And you know what? So radius is 4, as you remember. 4, 4, 4 radius. Where's the point 2i? 2i is somewhere here, and minus 2i is somewhere here. So what do we have? We have a very nice situation that both singularity points are inside our contour. So what can we do now? We need to calculate residues at both points, then to sum them together, and then, in other words, we need to apply the theorem. So let's start dealing with each point. So the first point is z1 is equal to 2i. And now we need to refresh our knowledge from previous tutorials how to calculate residue of our function in this point. Let's rewrite our function here. So this is our old task, but how can we do it? You know what? We had, if you remember, we had 3 methods, of course. The first method was was expanding into Lorentz series. But maybe you don't fancy expanding into Lorentz series, even though it's not very difficult for this function. But maybe you prefer method 2. Method 2 was to see that your function, it was only for poles actually. But we can try and apply. To be able to apply this method, we need to factorize this expression again, z plus 2i times z minus 2i. And what does our second method says? Let's recall our method 2 as to how to deal with poles. If your function f of z look like phi of z divided by z minus z0 to the power of n, where phi of z0 is not equal to 0, so it means that z0 is a pole of order n. To remember this beautiful idea. So the question arises: does our function require meet this requirement? Of course, you do have some experience now, and you can immediately spotted this expression which corresponds to this one. Now we have a suspicion that as this expression is in the power of 1, maybe this is the pole of order 1, simple pole. But you know what? We need to check the second, this requirement. So this whole expression plays the role of phi of z. If is our phi of z0 is not 0, let's check it. Let's check that phi of z0 is 2i. So let's substitute it here. 2 times 2i divided by 2i plus 2r. It's not 0, of course. It's 4i divided by 4. It's actually 1. It's not equal to 0. So our function could be viewed as complying these requirements. And that is why we can make a conclusion that z1 is equal to 2i is simple pole. In this case, we can apply our formula. Do you remember? It looked very terrifying, but after using it, after applying it for quite a few times, you get used to it. So if your z0, let me remind this formula, if z0 is pole of order m, then you can calculate residue in this pole using the following formula: 1 divided by m minus 1 factorial dm minus 1 dz m minus 1 of the expression which is f of z times z minus z0 to the power of n. But you know what? Oh, maybe not n, but m, of course. But you know what? In the case of pole, this guy is actually equal to phi of z, of course. So you can simplify this formula a little bit. Okay, so what is in our case? In our case, we are dealing with the simple pole. So our m is equal to 1. It means that this guy is 0 factorial is 1. I'm not even going to write it. And no derivative at all, because the derivative of order 0 means no derivative at all. So it's just function phi of z, which is given here in green, 2z divided by z plus 2i. And we need to calculate it in our point 2i. We actually did it before without knowing it. Okay, so 2i plus 2i. We have 4i divided by 4 each one. So we already have the first residue in the point 2i. Now we need to do something similar for the second point. Let's try it. So z2 is equal to minus 2i. And let me rewrite this function here again. So our function looks like 2z. Maybe I should write my expression, my denominator in the factorized form already. So this time we should have a look at this function at the different angle. So this time we are interested in this guy. This is plays the role of z minus z0 to the power of n. So again, maybe minus 2i is the simple pole again, but we need to make sure that the remaining expression. Place rule of phi of z, phi of z. So we need to check. We need to check. Let's check that phi in this point minus 2i is not equal to 0. So let's do it. Phi in point minus 2i, let me write it. Phi here, 2z divided by z minus 2i, and I need to substitute z with 2 minus 2i. What do we have here? 2 times minus 2i minus 2i minus 2i. This is minus 4i and this is minus 4i. So this is 1 as well. So it means that it is a pole. It is a pole of the same order. So z2 equal to minus 2r, simple pole again, simple pole. And so we can use the same formula again, but for the different point, of course. And you know what? This time I'm not going to write this whole formula, of course. So residue of our function f of z in the point of minus 2i will be equal to what? We are just no derivative again. No, this is 1 again. So, and this time we need to take phi of z, but we have different phi of z compared to the previous point. So phi of z looks like this now. 2z divided by z minus 2i, and we need to substitute z is equal to minus 2i, our current singularity point. But you know, when we were checking this condition, we just calculated the residue already, so I can easily write that this is equal to 1. Okay, now it's time to apply our theorem. So according to the residue theorem, the integral of our given function, which was 2z z squared plus 4dz along the contour is equal to 2pi. And now you need to add together this residue. The first residue was 1, the second was 1 as well. So our answer will be 4 pi I. So things are as simple as this, as you can see. No problem at all. So this was example of how you should use residue theory. Of course, I could give you lots of theorems, but lots of examples, but I think it doesn't matter because all you need to do, you realize that you need to really develop a good skill at calculating residues of singularity points. And for this, to this end, you need to do a lot of exercises from the first 3 tutorials. The first 3 tutorials were devoted to the same topic of how to determine the type of singularity point and how to calculate residues. So if you manage to master this technique almost perfectly, this calculation of contour integrals will seem like a piece of cake to you. And so, as for homework, you can take, there are lots of exercises actually in your study guide. So study guide, this is page 216 and 217, and exercises from 4.16 to 4.21. As you can see, there's plenty of exercises, problems there. And of course, you can finish questions from I think these are questions 4 and 5. And even question 3, you can do all these questions using residue theorem or Cauchy integral formula. I think that the residue theorem is the best one actually, but sometimes you might be explicitly asked to apply Cauchy's formula to calculate this given integral. So it means that you are supposed to know both methods, or even the first one, part of parametrization. As you notice in your tutorial sheet, question 3, even though it contains closed contour integral, but you are explicitly asked to to apply path parametrization. That means that you need to master all the 3 methods. Okay, so that's it. And the next tutorial will be the last one. It will be the part 1, which will be devoted to the remaining questions 4 and 6 in our tutorial sheet 12. I think that the recording will come maybe in a couple of days. So that's it.